Hello kids! Today, let me tell you a story. Once upon a time, there was a king who requested his minister to make the longest gold chain the world had ever seen. But that seemed excessive, so he settled for a chain that was 1 kilometer long. Now, the minister called the best 4 goldsmiths in the land, and they all started making it on a mountain at a height of exactly 1 kilometer. They all worked day and night until it touched the ground. 1 kilometer exactly. The day has come, and the minister went to the king and told the news. The king felt happy and ordered the giant to lay it around his fort, whose perimeter was exactly 1 kilometer. So, the giant's hand encircled the fort with this gold chain. But to everyone's surprise, the chain came up short by 100 meters. Then the king said angrily, "Get me the thief within a week, or you will be smashed by the giant hand." How was that possible? They had measured the chain before. It was perfect. Who stole the gold? Goldsmiths or the ministers?
Okay, so consider this. Say I have a rod with me. It's hanging vertically from the ceiling over here. Now, there is only one force that is acting on the rod right now, right? It's the gravitational force under its own weight. We can even say that this gravitational force is the force responsible for the longitudinal deformation of this rod. However, this force isn't really the typical kind of force applied evenly on a single point. In fact, the force or tension applied by the rod is different on different points, and it varies depending on the mass hanging below the point we considered. Let's first consider the extreme points. The highest point of this rod is the one that touches the ceiling. The rod is fixed to the ceiling and it has to balance the full weight of the rod from that point. Now, if we consider the lowest point, there is nothing below this point. Basically, this lowest point of the rod has nothing pulling it down. So, there is no force applied on the lowest point at all. With that, we can say with confidence that the maximum stress will be exerted at the highest or hanging point, and the minimum or no stress will be exerted at the lowest point of the rod.
What is he explaining? I didn't understand anything. All stupid physics terms. Now I'll explain. See, this is a slinky. It expands. The top part expands more than the bottom part, right? The top part has more weight under it. Bottom part has nothing under it. So top expands more than the bottom. The same thing he is also explaining. I am also telling the same thing.
To find the tension at any general point in the rod, we need to consider how much part of the rod is hanging below that point. Then, just balance the tension with the gravitational force due to the mass hanging below it. We will find the tension in the rod at any general point later in this video. Since we know the tension across this rod is variable, we can't really apply Hooke's law directly into this. Rather, we need to take a different approach. So, what we do is we consider a small element dx of rope at a distance x from the lower end. Then we will find the elongation in this small element dx using Hooke's law and add all the small elongations throughout the entire rod by using integrations. Here we see that force or tension that is applied by the lower part of length x on the small element is the weight that is on the lower part. But how do we find that out? We start out by finding its mass. It's easy to find the mass of this lower part using the unitary method. Notice here that the total mass is m for a total length of L, right? This means that mass per unit length is m by L, very simple. So, the mass of length x would be m by L times x, which is just mx by L. We got that by multiplying the mass per unit length with the required length x. As we know, to get the weight of an object, what we need to do is we need to multiply the mass of that object with g, acceleration due to gravity. Let's apply this. So we get the weight of that part as mg into x by L. The weight of this part is counterbalanced by the tension from the upper part. Now, how do I know that?
What does he know? Explain. Okay, I'll also listen. Explain.
Because the rod is not moving up or down. The downward force must be equal to its upward force, which is tension. Which means that tension should also be equal to mgx by L. This is the tension which we consider responsible for deformation of dx element. Since we know that stress is equal to tension by cross-sectional area, we can then substitute what we got from earlier. If the cross-sectional area is A, then we can say that stress is equal to mgx by L divided by A, which is mgx divided by L into A. If we consider the increase in length for dx to be, let's say, dy, now we know that strain is defined as a change in length divided by the original length. Knowing this, let's plug in our values. Our change in length is dy and our original length is dx. Altogether, we can say that strain is equal to dy over dx. Knowing the strain can also help us find Young's modulus. Since we know that Young's modulus is stress divided by strain, plugging in the values we already have for stress and strain results in getting this formula. Which is y equal to stress divided by strain, which is equal to mgx dx divided by LA dy. Now cross multiply this. You get y into dy equal to mgx into dx divided by LA, which can also be written as dy equal to mgx dx divided by LAY. See that this is capital Y, which represents Young's modulus. It has nothing to do with the small y. Okay, but you do need to remember that dx is just a small part of the entire rod and dy is just a small change within that small element. To get the change of the length of the entire rod, you would need to calculate the sum of all these small changes within the small elements of this rod. In mathematics, we have a technique for doing such additions, which we call as integration. We can integrate all the small changes from the length x equal to 0, the bottom part, till x equal to L, which is at the top part. Now, integrating the equation on both sides to get integral dy equal to integral of mgx by Lay dx, where this x can be taken anywhere from 0 to L. Clearly, integral dy, that means adding up all the small elongations, will give you delta L, that is the total change in length of the rod. So, now solving the integral using the integration formula for power law and applying the bounds, we get delta L equal to mgl square divided by 2Lay. Now simplify this and we'll get delta L equal to mgl divided by 2Ay. This delta L is the net change in the length of the rod by its own weight. This is the amount of expansion that a rod can undergo due to its own weight. Now, you can also consider a rope or even a Spider-Man's web instead of the rod here. Here is the question to ask yourself. If you have a very big rope tied vertically, will it break in the middle or will it break at the top? If you have understood the video here, you should be easily able to answer it. So, I'll leave that to you and I'll see you again in the next video. Until then, bye-bye.
I am sure you wanted to know what happened to the king's gold chain. After the king's warning, the minister took it on his pride and started inquiring the goldsmith's personal life. Researched the ancient books of wisdom. Days are ticking away and the deadline of that week is approaching. Suddenly, he realized he missed the physics in it. The next day, in the king's court, the minister was brought in front of the king. Minister then explained to everyone.
You see, what happened was, when the chain was suspended from the mountain, it had expanded under its own weight, which is why it seemed to be 1 kilometer. But when it was laid flat on the ground, there was no expansion due to gravity.
And that's when the real length of the chain could be measured. And that, sadly, came up to 900 meters.
The king was obviously still angry, but the queen consoled him and gathered more gold to fix his chain, and also praised and rewarded the minister for his talent. In the end, all became peaceful in the land of the king, and no innocent was punished, because science had once again saved the day.